that the radio direction is described by the unit vector A rho. Therefore, to find the unit vector in terms of x direction, which is now this, we want now to find our AX from those two directions that we have just defined of A rho and A phi. We are saying that the unit vector AX is going to be the hypotenuse that is made by this vector A rho and this vector A phi, and you can see that A phi is in the opposite direction of its default one. Therefore, we put a negative. This negative A rho phi, A phi and A phi is the same one. So we are saying that if you go 1 unit that direction of A rho, or negative 1 unit of A phi, you will have 1 unit AX. This is from this point to this point. So that is going to be my unit vector AX. And how can we determine the value of AX? Just do some additions by saying that, oh, I think I'm writing too many things here. So I think I will delete this and see that doesn't bring much confusion. I had drawn a straight line here. So just for my illustration, I had said that if this angle is theta, using our ideas of trigonometry, if this line is parallel to this, to AX, therefore you can say if this is angle theta, this side is also angle phi. Sometimes I confuse phi and theta. And by another rule of trigonometry, this angle is going to be phi. And therefore, this angle, which is now describing the angle between A rho and AX, is going to be phi state. And if you are to do some similar trigonometric expressions, you can also find that this angle is going to be A phi. And therefore, you can say that using the basic ideas of cos and sine, we want to find this distance from this point to this point, and that distance is going to be given by sine phi sine phi is going to be given by that small x prime, I think I can call it x1, divided by hypotenuse, which is negative A phi cap. Therefore, if you take this on this side, you have negative A phi cap, and this one goes. Therefore, we are left with our small portion of x. I'm calling x prime, and it is given by negative A phi cap sine phi, and that is the one that you will see I have written here. Then the other x prime 2 can be expressed by, I said by doing some mathematics, you'll see that this is going to be angle phi again, and therefore you say cos phi is equals to the adjacent, which is x prime divided by hypotenuse, which in this case is A rho cap. And therefore my x prime becomes A rho cap cos phi. That now gives you this idea of the second one. So what we are saying is that we can express now the full AX to be, we are saying that X or AX, the unit vector, is going to be my x1 plus x2 x prime, and these are the ones I have found right there. And so I believe that becomes a bit clearer. It is a bit technical, but you actually see that we can express AX as cos phi A rho minus sin phi A rho. And similarly, you can find AY using another diagram that we have drawn here. That now we want to find, I think we can draw this one somewhere else that will allow us to have better illustration. I want to copy this and take it somewhere else so that we can use it for illustration. Oh, what is happening? What I copied it. Things have started not behaving very well. We are 68. Yeah. So I wanted to use this bigger screen for illustration, just in case some people might have got lost. We are saying that now we want to find the unit vector A, Y using the cylindrical coordinate system. And we already defined A rho to be the radial distance, that one. And we have already seen that we can express A phi using that direction. And therefore, we definitely know that 2 unit vectors of cylindrical are going to be are going to give us the unit vector AY. So this is the one, this is my unit vector AY right there. You can see, but it is made up of 2 portions, Y prime and Y prime prime. So to find Y prime, you can say that I have just done similar mathematics like I showed you earlier, that this is 5. Therefore, this angle is going to be minus 90 minus 5. The same one going to be here. Therefore, this angle is going to be minus 5. And this is going to be minus 5. 5 is going to be 5. And similarly, you're going to have this to be 5. Therefore, if you want to find Y prime, you can simply say this is going to be given by what? Sine of A rho, sine of phi A rho. If you don't know how we have done that, we have just said sine of phi, this phi now. That phi. Sine of phi is going to be opposite, which is Y prime divided by the hypotenuse, which is A rho. This is my hypotenuse, A rho. And this is my angle phi. Therefore, if you do that, you can of course take this to this side. You are going to find that sine Y prime is going to be sine phi A rho. Similarly, Y prime prime, which is now this one, can be obtained by simply saying that it is equals to hypotenuse, which is now A phi, or rather, I start with cos of phi, then A phi. And therefore, you would say that AY is equals to Y prime plus Y prime prime, which you have seen to be given by sine cos phi A phi plus, I think I have just interchanged them, doesn't matter, sine phi A rho. So again, very lengthy illustration of the points. We were just trying to show how we are getting this and this, and these are the ones that are saying that you can be able to express AY cap in terms of the unit vectors A rho and A phi. And again, since we said that Z for X and okay, for the Cartesian and cylindrical are the same, therefore we say that the unit vectors are going to be the same. Now you can also do the opposite by expressing A row from AX and AY, and you can do very simple mathematics. Add these two. Add yeah, add this one. You're going to find A. This doesn't do very well. Let's try that very quickly. I copy that. Take a snapshot of that. I want us to do confirm that you can still do that simple manipulation of mathematics by coming right here. And I'm saying that if you said you added the right terms together, AX is equals to cos of phi A row minus sine of phi A phi, and AY is equals to sine of phi A row You can go, Eric. We have had your concern. Plus cos phi A phi. So if you just add these components, you're going to have AX plus AY is equals to A row to bracket cos phi plus sine phi plus A phi to bracket cos phi minus sine phi, and further manipulation by I think this might take a bit longer to do, so I'm not going to do that now. But we are saying that following similar ideas like we have done for this one, we can still be able to express the Cartesian unit vectors in terms of the cylindrical unit vectors right there. And I can leave that as an assignment for you. Okay, not going to be examined, but to make sure that you can be able to do that on your own. Yes, so I think we want to move a bit further because we have dealt sufficiently with the unit vectors. So I want now to move to the vectors themselves, so that we are saying that we can express A in terms of the unit vectors A row, A phi, and A z, given that we were already operating on from the Cartesian coordinates. So this is the idea that we have, and we are saying that we can do that by getting equation 2.9, this equation that we have just derived, and then you replace them in equation 2.2, which is right here. So if the copying is not coming out very fast, so but we can still do that. New. This is my equation 2.2, and I am putting it here, and I want to get to equation 2.9. That we have just found out they are right here. So if we paste them here, so we are saying that if you wanted now to express our vector A, which was defined in x coordinates, x, y, z coordinates in terms of its error, we would simply say that A is equals to AX, but now this is, we replace AX using its equivalent cos phi, A raw minus sin phi, A phi plus AY. AY is then into bracket sin phi A raw plus cos phi A phi and plus AZ. So if you just factored this out, you want to factor common factors or common factors. This is called common factors. Yeah, like terms. You get the like terms, and then you have a vector, which is always remember to put the arrow, is going to be given by. I can put my arrow outside. Then I say AX cos of phi plus AY cos of, not cos, let me get a rubber. What? And I get AY sine of phi. Then I say plus A phi to bracket. Now this one is going to be minus AX sine phi plus AY cos of phi, then plus my AZ. And therefore we are saying that my arrow, this becomes my arrow, which is equals to AX cos, this becomes that. So arrow becomes AX cos phi plus AY sin phi. So, and you can do the others for arrow, which is this guy right there. And therefore we can simply say that arrow is going to be equals to minus AX sin phi plus AY cos phi. So we have just seen how we can express the scalars in the form that I have just shown you, and that these are the equations that we are trying to derive, how you can express the scalars arrow, A phi, and AZ from the Cartesian system that we have just illustrated. And you can express now this in terms of matrix, and I believe you have done some matrices. If you have not done, you may do some revision of matrices. I'm not going to do that because our unit is not on mathematics. Rather, it is on vector. It's not on electromagnetics. These are just giving you the tool that you need. And you can do the reverse. You can attain, this was attaining you the cylindrical scalars for each unit vector. And now you can get now the Cartesian form from the reverse of what we have done in terms of arrow and A phi. We are not going to do that. And that gives you vector to vector transformation of a vector from Cartesian to cylindrical and from cylindrical to Cartesian. So this is something you can do without blinking an eyelid. So, and similarly, this is the mathematics I told you earlier about the axioms. You know what happens when you dot AX dot arrow, and this actually is, even the authors say that if you want to derive that, you can do that on your own. That is sufficient to talk about cylindrical, and that gives us some time now to talk about spherical. At that point, again, I will pause, allow people to ask questions and raise concerns. And if all is good, you can also comment on chat. Continue. If it is good, if you don't have a question, you can just say, I'm fine, all understood. I'm waiting. Say something. I need to confirm that you are on board, all of us. Yeah, Corinne Zomoti, thank you. You are saying you are good. Purity is always our good ambassador of students. She always tells us what's happening. Fine, thank you very much, Purity. Aldenis, Kipchai, Lawrence are responding, and I think that is how we need to go. Our last small subsection that we want to discuss is in regard to spherical coordinates. We should finish this class by 12 as scheduled. Faida Kinyi, asante sana. Martin Gige, all good, so far so good from Tom Mutua. And the rest of Faida Kinyi, Tom Mutua, you need to put your registration number. Nobody will say you attended the class. And somehow these things are important. As much as I can insist on them, you need to have your registration number as part of the attendees. So make sure you put it there. All right. Francis Mwaniki, you're saying all good. I'm good to hear that. So we continue. Spherical coordinates. We are going to be describing the spherical coordinates in terms of R for radius, beta, and we are going to find that theta is also called colatitude. It is similar to the one that we use to describe latitudes in the map. And then you're going to have phi, describing the angle from x towards y. So these are the three parameters or the three dimensions you're going to work with. And you're saying that the spherical coordinate system is most appropriate when one is dealing with problems having degrees of spherical symmetry. And A point can be represented as shown in figure what? Figure 2.4. Figure 2.4 is here. So as I mentioned, I think we have already seen this somehow, but I have copied it here. I think we have done so many things until we have overtaken ourselves. Yeah, here. So I want to paste it here. And you're saying that R is the radius. R is equivalent to rho. You know, we say radius, this is for cylindrical, for a cylinder. We describe the radius with rho. But now for the sphere, we describe it with R. The same angle, remember, the same angle we had for cylindrical, we are going to have it for the sphere. The same expression, phi. Phi is describing the angle when you move from x towards y. And so that is phi. They might be similar, except there's an important difference. Cylinder, spherical. Except that in sphere, this becomes the third dimension, but in cylinder, this is the second dimension. That is the only difference.